Hi everybody, I hope this video finds you well. In today's video, we're going to be working our way through the Practice 3, which is the practice sheet that deals with the normal distribution, relative position, and statistical bias. If you haven't already finished the videos for the normal distribution, relative position, and statistical bias, or if you haven't had a chance to work through these questions on your own, I'd pause this video, go ahead and try these yourself, and then once you've attempted each of these three questions, then go ahead and watch through this video. If you've already attempted these questions and you're ready for that discussion, well, let's get started. So for question 1 here, we're studying the amount of time that adults spend standing or walking per day. We find that amongst fit adults, the time is approximately normally distributed. So we have that it's normally distributed. That's key information, with an average of 550 minutes and a standard deviation of 115 minutes. Remember, when we know that a population is normally distributed, then all we need to know about that population to fully define it is its average and standard deviation. And in this case, the time that fit adults spend walking or standing per day is normally distributed, and we have its mean and standard deviation. We also have in this question that amongst mildly obese adults, the time is also approximately normally distributed. So we have that again. And now we know that the average for this population is 360 and the standard deviation is 70. So we've got two populations, but both of them are normally distributed, and we have the mean and standard deviation for each. The first question asks what percent of mildly obese adults stand or walk for less than 550 minutes per day. So to do A here, we can go ahead and start by drawing ourselves a bell-shaped curve. We know that because this population is normally distributed. We can label the middle at the average. Since we're talking about mildly obese adults, we know that that average is 360 minutes. So we can put the 360 in the center here. We're interested in the percent that stand or walk for less than 550 minutes. 550 is definitely larger than 360, so it's somewhere over here to the right. And we're interested in the people who stand or walk for less than 550 minutes. So the area under this curve, remember the area under the normal curve represents the percentage of the population that has that trait, that we're going to be interested in is all the stuff to the left here. And again, we're interested in that area to the left because it specifies less than 550 minutes. All right, we can go ahead then and calculate the z-score. The z will be our data point, 550, minus the mean, 360, divided by the standard deviation. And again, since we are working with the mildly obese adults, the standard deviation will be 70. So we'll put a 70 in the denominator. Up top, we can do that subtraction first. So 550 minus 360. We should get 190 divided by 70, and then we can actually do that division, and we should get a z-score of about 2.71. So notice that z-score does make sense. It is a positive z-score because 550 is above the average. Now we can go ahead and look this up on table A. So let's go ahead and do that. I put table A at the end of this document, so we can go ahead and look for that. 2.71. So let's go ahead and look for that. We'll need the positive sign. So there's 2.7, and if we zoom out a little bit, there's 2.7 and 0.1. So we should find 0.9966. So 0.9966. So if we look that up, we find 0.9966. Remember, table A always tells you what's to the left. So on our diagram, we can fill that out as this way, 0.9966. Does that match with our shaded area? Yep, we wanted the stuff to the left, and we found the stuff to the left. So we just need to translate this into a percentage. We can say that 99.66% of mildly obese adults walk/stand for less than 550 minutes per day. There we go. So close to 100% of this population walks or stands for less than 550 minutes per day. Okay, let's go ahead and take a look at B. For B, we want the percent of fit adults, so we're going to change populations, that stand or walk for more than 600 minutes per day. So let's give ourselves a fresh page to do that. So this will be part B here. So again, we're looking for the percentage of fit adults. Remember, fit adults were normally distributed, mean 550, standard deviation 115. So let's go ahead and draw our bell-shaped curve. We'll label the middle at 550. We are again interested in part B for those who walk or stand for more than 600 minutes per day. 600 is a little bit above 550, so we can do that. And then we are interested in the people who spend more time than 600 minutes. So we'd be shading in this area here to the right. All right, we can go ahead and get our z-score as normal. Our observation is 600 minus 550, which is the mean, and then we need to divide by the standard deviation. Since we are working with the fit adult population here, we want to use the standard deviation of 115. So we'll divide by 115 there. That's going to be 50 over 115. We can go ahead and do that. 50 divided by 115 should give us a z-score of approximately 0.43. All right, notice again, we do get a positive z-score because 600 is above the average. Now we can go ahead, look that up on table A. So we're looking for technically 0.43, so 0.4 and that 3. So let's go ahead and find that. So there's our 0.4 and our 0.3. We intersect those together. Looks like we find 0.6664. So after looking this up on table A, we find 0.6664. Again, remember table A always tells us the area to the left. So on our diagram, we can fill that in this way, 0.6664. Notice this time this area does not match what we shaded. So how do we find this blue area? Well, we need to do 1 minus because the total area is equal to 1. So the shaded area is going to be 1 minus 0.6664, which gives us 0.3336. So there's our shaded area. And remember, we're subtracting it from 1 because the area under the entire curve is equal to 1. All right, now we just need to translate that into a percentage. We can say that 33.36% of fit adults spend more than 600 minutes per day walking / standing. There we go. So we got the percentage of this population. Notice it doesn't apply to the other population of mildly obese adults. It would apply only to the population of fit adults here. All right, for part C, let's see what we have there. For part C, we want the percentage of mildly obese, so we're going to go back to our other population who stand or walk for between 300 and 400 minutes per day. So we can start again with a diagram. We'll go ahead and put the middle for the average for the mildly obese population, which was 360. So let's go ahead and put that on. Then we're going to be interested in the mildly obese adults who spend between 300 and 400 minutes walking / standing. So 300, it would be a little bit less than 360, so that might be 300, and 400 would be a little bit above. And the shaded area we're going to be interested in is the people above 300 but below 400, so the area between those two values. We're going to have to go ahead and find two z-scores. So z1 will be for the lower number, 300 minus the average of 360, divided by the standard deviation, which if we go back and check, was 70 minutes for the mildly obese population. So we can divide by 70 there. Numerator is going to be minus 60 divided by 70. Negative 60 divided by 70, we should find that as about negative 0.86. So we're going to look this up as negative 0.86 on table A. So let's go ahead and do that. So we go to table A, zoom out a little bit, negative 0.86. So zoom out a little bit more. There's our negative 0.8. There's our 6. So if we put those two together, looks like we should find 0.1949. So for this one, after looking up on table A, we can find 0.1949. Okay, let's go ahead and find Z2. So Z2 will be 400 minus 360 over 70, which is 40 over 70. If we do that division, we should find a z-score of about 0.57. Notice that this time it is positive because 400 is above 360. Also notice that in magnitude, 0.57 is smaller than 0.86 because 400 is closer to 360 than 300 is. Okay, let's go ahead and look that up on table A. So again, we're looking for 0.57, so 0.5 and 7. So we'll go to the positive side. There's 0.5, there's 0.7. So we put those together, and we get 0.7157. So 0.7157. So 0.7157. All right, now we can go ahead and put those onto our diagram. Remember, table A always tells you what's to the left. So we know that this stuff this way must be 0.1949, and this stuff this way must be 0.7157. How do we find the stuff in between? Well, if we take this and we remove this, then we'll just get the stuff in between. So in this case, we can say that the shaded area is going to be 0.7157 minus 0.1949. If we do that, 0.7157 minus 0.1949, looks like we should get 0.5208. Translate that into a percentage, and we can say that 52.08% of mildly obese adults walk/stand between 300 and 400 minutes per day. So there we go. So there's our calculation for that. Perfect. So these first three, A, B, and C, all did different percentages below, above, and between two values. These are the percentages you should be comfortable calculating using the normal distribution. Part D is going to be a little bit different. Part D sort of is the reverse of this. So Part D says that we have Tom, who is a fit adult, so we know which population he belongs to. He's in the 93rd percentile in terms of the time he spends standing or walking per day, and we want to know how long he actually spends walking or standing per day. So this is going to be a reverse process. So let's go ahead and see how to approach this. So for D, he is a fit adult, so we should use the average that applies to fit adults, which was that 550. So 550. Now we know he is at the 93rd percentile, since that means he's far above the average here. So we can put him located maybe somewhere over here at X. And we know that this percentage of people who do not walk or stand as much as he does, all that area there, that has to be 0.93. So what are we going to do? Well, we're going to locate 0.93 on inside of table A. So we are going to look for the closest thing on the inside of table A to 0.93. Let's go ahead and see if we can do that. If we go to the positive sign, right, we can see that there's some like 0.82s, 0.87s, 0.91s. Remember, we're looking for 0.93. There's 0.9292. There's 0.9306. So 0.93 should be right there. Technically, 0.9306 is a little bit closer, so we want to use this one. Notice if we go out from there, we get 1.408. So the z-score should be 1.48 here. So to summarize that, what we found is closest value was 0.9306, and as we saw, 0.9306 went to 1.4 and 0.08. So what that meant is that our z-score, or Tom's z-score in this case, is 1.48. Now how does this help us? Well, now we can set up our standard z-score formula and solve for the amount of time this person walks or stands per day. So we can say 1.48 is equal to x minus the average, which is 550, divided by the standard deviation. Remember that since Tom is a fit adult, we would use the standard deviation of 115. So divide by 115 there. We can start off by multiplying both sides by 115, so 1.48 times 115. That would give us 170.2 equals x minus 550. Then we add the 550 over onto the other side, and we should get 720.2 equals x. So what does that mean? Well, that means Tom stands / walks approximately 720.2 minutes per day. So there we go. We were able to actually find the value of the variable for this individual based on their percentile rank. We called all of this the sort of reverse process, right? Where instead of trying to find the percentage, we knew the percentage, we used the percentage to get the z-score, and then we solved the z-score formula to actually get the value of the variable. All right, we've got one last piece to this, which is part E here. So for part E, we have two people, Aaron, who is a fit adult who stands and walks for 690 minutes per day, while Walter is a mildly obese adult who stands or walks for 480 minutes per day. So we want to know which person stands / walks more relative to their health group. So this is a relative position question, so we're going to be using the z-score. So let's go ahead and do that here. So we're going to calculate two z-scores. So the z-score for Aaron is going to be the 680, which is how long he walks, right? We said that Aaron, 690, excuse me. 690. That's how much time he actually spends doing this. Then remember, Aaron should be compared against other fit adults, so an average of 550, standard deviation of 115. So 690 minus 550 divided by 115. You can see that he walks 140 more minutes per day than average, divided by 115. And you can see that he is about 1.22 standard deviations above average. Walter, on the other hand, we can see spends 480 minutes per day. So if we do that, we'd have 480 minus, but he should be compared against mildly obese adults who have an average of 360 with a standard deviation of 70. So we're going to be doing 480 minus 360 over 70, which is 120 over 70. 120 divided by 70 yields a z-score of approximately 1.71. If you want to visualize these numbers a little bit further, you can certainly draw yourself like a number line. There's 0, which would mean that you're average. Maybe there's 1, there's minus 1. Aaron is 1.22, so he should be right about there. And Walter is 1.77, so he might be right about there. Now, in terms of the time you spend walking or standing, it's saying who walks or stands more relative to their group. So, of course, this would be more here because you're further above average, and this would be less over here if you were below the average. So we can see that even though Walter only stands for 480 minutes per day compared to 690, he is further above the average relative to the standard deviation for his health group. So we would say Walter stands / walks more relative to his health group. So again, that's not saying that his actual time is more. His actual time is 480, which is definitely less than 690, but it is more relative to his health group, so relative to the average and standard deviation for people similar to him. So there we go. In this first question here, we looked at calculating percentages based on the normal distribution, sort of 3 different situations: less than a particular value, more than a particular value, between 2 values. We also saw how to reverse this, taking a percentile and changing it into a value for the variable. And then finally, we also talked a little bit about relative position. These are all the major things you should be comfortable with when working with normally distributed data. All right, let's move on to question 2, which intersects some of the theoretical work with normal distributions back to what we learned about how to actually work with quantitative data. So for question 2, we have a researcher that is studying IQ scores for adults. So to study this, the researcher randomly selects 16 adults to take an IQ test. The researcher then records each of their scores and gets the following data. And we're going to imagine that these IQ tests, they're scored in points. So we had somebody get a 78, 85, 93, all the way up to a 132. So we're going to do some basic descriptive statistics, mean, median, standard deviation. We're going to look at a stem plot, and then we're going to talk a little bit about how we would use the empirical rule if it's appropriate to do so. So to start off with, we'll go ahead and I'm just going to grab this data so that we can see this as we're referencing it. Let's go ahead and do so. Okay, so let's give ourselves another page. So this will be question 2 here. Go ahead and paste in our data. Okay, so there's our data set. So for part A, we want the mean, median, and standard deviation. So let's go ahead, we'll take all this stuff and we'll throw it into list 1. So if you have your calculator, stat, edit, to clear out any data that's in there, we can type these in: 78, 85, 93, 94, 98, 99, 100, 102, 104, 105, 108, 110, 113, 117, 123, and 132. We can check when we're on that 132. It should say L1 of 16 because we typed in 16 data points. Then stat calc 1 var stats with L1 as our list. We can get that the mean here should be approximately 103.8, and I guess that would be in points. The median, if we scroll down a little bit, should be 103 points. And the standard deviation, of course, we'd want to use the sample standard deviation here, should be 13.6 points. Notice a couple things, right? This is a good sign that the data is at least going to be symmetric, so either normal or uniform, because the mean and median are very close to one another. For B, we'd like to build a stem plot. No need to do a split stem plot, because for stems, we're going to have 7, 8, 9, 10, 11, 12, and 13, so no need to split it. So we'll just do a normal stem plot: 7, 8, 9, 10, 11, 12, and 13. For the stem of 7, we had a leaf of 8, then 5, 9, 3, 4, 8, 9, then 0, 2, 4, 5, 8, then looks like 10, 13, 17, that 23, and that 32 there. We'll include our key. 7/8 in this situation means 78 points. What sort of shape are we seeing here? Well, we can see that we've got sort of a tail, then we've got sort of this tall middle section, and then another tail. This would be roughly bell normal here. So again, we sort of knew that it should be a symmetric distribution, so either bell normal or uniform. Clearly, we have sort of a tall peak in the middle, and then we have tails out to both sides. So approximately bell normal here. All right, let's see what else we need to do. For part C, we'd like to know, is it appropriate to apply the empirical rule? Well, we can make that decision now that we know that the shape. We can say yes. Empirical rule can be applied since data is approximately normal. Right? If the distribution had shown a right skew, left skew, uniform distribution, we wouldn't be able to apply the empirical rule, but we should be able to in this situation because we have normally distributed data. All right, for part D, it says, according to the empirical rule, between what two values should 68% of the data land? Well, we know, according to the empirical rule, 68% should be in, well, in words, we know that 68% should be within one standard deviation of the mean. Notation, we would say x bar minus s to x bar plus s. If we wanted to know about 95%, we'd use two standard deviations, so x bar minus 2s, x bar plus 2s. If we wanted 99.7, we'd do x bar minus 3s, x bar plus 3s. But since we specifically said 68%, we'll only go one standard deviation in each direction. We can fill in those values. Our mean was 103.8, and our standard deviation was 13.6. And then we'll do 103.8. and then we'll add 13.6. So for the low end, 103.8 minus 13.6, we should get 90.2, and for the high end, 103.8 plus 13.6, we should get 117.4. So 68% of the IQs that we measured should land in that range. Let's see what percentage actually does. So part E says what percentage of the data actually lands in the interval we found in D. So this just means we need to count up our data points. So if we do this, say, in red here, 90.2 to 117.4. So 90.2 would catch all of that stuff. 93 would be in there. And we set it all the way up to 117.4. So 117 would count. So what does that mean? Well, we're missing these two and these two. Now, we know we had 16 data points, so that must mean that there's 12 in here. We can also just do that by counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we would have 12 out of the total number of data points. We had 16 data points. And if we do that, 12 divided by 16, we should get that that is 75%. So it was a little off here. We said that we should expect 68%. We actually ended up getting 75%, so a higher percentage here. And that's probably due to the fact that this middle has more data and these tails get smaller faster than a true normal distribution would. But again, for a small data set, our prediction is not that far off from what really happened, which shows you again how this theoretical stuff can really apply even to real data sets. Okay, so this question here, question 2, was all about sort of making sure we're still comfortable with the basic descriptive statistics of quantitative variables, and also how to sort of analyze the accuracy of something like the empirical rule when applied to an actual data set. All right, let's turn our attention then to question 3, which focused more on biases as well as some basic terminology from early in our class. So in question 3, we're going to suppose you work for a large coffee shop chain that has stores all across the US. You're tasked with investigating how satisfied your employees are with their working conditions. So to do this, you randomly select 20 of your shops from across the US and survey every employee at these shops. So you ultimately survey 500 employees. So you select 20 shops, but obviously a lot of the shops have more than one employee. So you end up talking to 500 employees, but only 80 of them respond to you. For each of the employees, you identify yourself as a member of the corporate headquarters, and you ask them, considering how hard this company works to give its employees the best possible job experience, how satisfied are you with your job here? Very satisfied, satisfied, not satisfied. So you get the following data. So 38 people said very satisfied, 31 said satisfied, and 11 said not satisfied. You'll notice that if we add those up, if we take 38 plus 31 plus 11, we do get 80, which makes sense because we know only 80 people responded. So let's do a couple things with this. First, we want to go ahead. You know what? Let's just so that we can reference this. This shouldn't take too much space. Let's just grab this real quick. Take a screenshot of that and copy them. Okay. Okay, let's go ahead and we'll give ourselves one more page. So this will be our work for question 3 here. Okay, that should be large enough to sort of generally read. Okay, so there we go. So let's go ahead and take a look at this. First thing we want is population of interest. So notice we said that you're working for this coffee shop chain and we're investigating how satisfied your employees are. So we would say that the population here would be all the employees at this coffee shop chain. Okay, what's our sample? Well, the sample was intended to be 500 employees, but we only got to actually talk to 80 of them. So our sample would be those 80 employees we actually talked to. What sampling technique was used to build our sample? Well, remember, we weren't randomly selecting individual employees. We selected 20 shops and tried to talk to everybody at those 20 shops. So this would be an example of a cluster sample. Why is it cluster? Again, well, the choice, the number of selections this researcher made, or we made in this case, was only 20 selections. But we ended up getting 80, or we tried to get 500 individuals. So every selection we made added a bunch of individuals to our sample. So the clusters here, each shop. So each shop maybe had 10, 20 employees. So every time we selected a shop, we added a bunch of people to our sample. All right, we're going to construct a relative frequency table and draw a bar graph for this data. So that's sort of the old descriptive statistics of that. Remember that to do this, we will need to divide each of these frequencies by the sample size, which is 80. So we'll have the sort of response and the relative frequency. So very satisfied, satisfied, and not satisfied. Let's go ahead and do those divisions. 38 divided by 80. We should get 47.5%. 31 divided by 80. We should get, after we round, 38.8%. And 11 divided by 80. We should get 13.8%. So there we go. There would be our relative frequency table, writing everything as percentages. We can go ahead and construct a bar graph for that. So we'll put the relative frequency here in percent. We can go 10, 20, 30, 40, 50%. So I've got to have a consistent axis here. Okay. Then remember, for a bar graph, the bars should not touch. So there's very satisfied, and we'll bring that up to 47.5 about. You know, satisfied should be 38.8, so pretty close to 40. And then not satisfied, 13.8. So there we go. So again, remember, in a bar graph, those bars should not touch, and this was level of satisfaction. Might be tempted to say something like, oh, maybe this shows a right skew, but remember, shape and distribution, that applies to quantitative data only. So there's no shape or distribution to categorical variables, so we wouldn't say anything else. We just want to build the diagram here. The reason that there's no shape or distribution applied to categorical variables is because there's no reason we have to do very satisfied, satisfied, not satisfied. We could have put them in any order depending on how we wanted to order the categories. So there's no sort of intrinsic shape to this stuff. So never mention shape or distribution when working with categorical data. All right, let's answer another quick follow-up. We wanted to know what percentage of people surveyed said they were either very satisfied or satisfied. Remember, or just means to use addition. We have those percentages right here, so we can do that as 47.5% plus 38.8%. And if we do that and just sum that up real quick, we can see that this would give us 86.3%. So in other words, 86.3% of the people we talked to ended up saying they were very satisfied or satisfied, which I suppose from a company's perspective would make you pretty happy. That means most of your employees are either satisfied or very satisfied with their working conditions. In part F, we wanted to talk about sort of the newest topic that we've discussed in our class, which is statistical biases. So what biases are present in this data? Well, remember, we have those 7 different biases that we discussed. We talked about things like undercoverage, voluntary response bias, general response bias, interviewer bias, wording bias, ordering bias, and non-response bias. So what are the sort of major things we could talk about here? Well, the first and easiest to identify should be non-response. How do we know there was non-response bias? Well, only 80 out of 500 responded. That's an incredibly low response rate. If you wrote that out as a percentage, 80 divided by 500 means that only 16% of people who you contacted responded to you. So this definitely has non-response bias. This is all you would need to write to justify that, right? Saying only 800 out of the 500 that you asked responded. So certainly non-response bias. Second, it's probably an issue, right, about the fact that you identify yourself as a member of the corporate headquarters and then ask them how satisfied they are with their job. So certainly we can imagine that there is an interviewer bias. Right? That it's the company asking about satisfaction. Right? Now, this could easily have been solved by having like an anonymous survey or something like that, but that's not how this was done. You had an interviewer that literally identified themselves as being from the corporate headquarters, asking the people this question. So that's certainly going to influence some responses. People are going to be unlikely to say that they're really unhappy, probably to the face of somebody who's from corporate headquarters. So certainly some interviewer bias. We can also take a look at the question that was asked, right? Notice that the question has this unnecessary language here, considering how hard this company works to give employees its best possible job experience. Yeah, none of that should be in there, so that means there's also wording bias here. That whole thing where it says, considering how hard, blah, 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 right? That's unnecessary and loaded language. Why would we consider that loaded language? Well, right in there, it frames the company in a positive light, saying that this company works really hard to give its employees the best possible job experience. But that might impact how people answer about the thing that we're actually trying to study, which is how they feel about their satisfaction. So it's really not a good idea to have all that unnecessary language there. You just want to ask, how satisfied are you with your job here? And then give them these choices. That would be a much better way to phrase it. Are there other issues? Well, I think it gets harder to justify the other forms of bias. Under coverage, there's nothing really given to us in the text here that would justify that we missed a certain population. I mean, we randomly chose some shops and we talked to all the people from those shops. It doesn't seem like there's anything fundamentally like under coverage. Voluntary response bias is an absolute no here because we selected the people. Some of them chose not to respond, which is why we had non-response bias, but we certainly can't have voluntary response bias because we did do the selection. Remember, voluntary response bias only happens when people put themselves into the sample. You could maybe argue for general response bias. You could say maybe answering questions about your job satisfaction is personal or sensitive. I might think that that's acceptable, but I think the interviewer bias is certainly a much stronger justification there. And finally, the only other one we didn't talk about was ordering bias, which unfortunately, again, we don't really have any information about because we don't know if there were any other questions in the survey. So I would say that these three are the three main forms of bias that we could justify based on the information given to us. So that wraps up the practice problems for practice 3.